Good morning and welcome to Tech 259 on Monday, April 5th. I have some good news today, and that is that the topic for today is DC generators. And DC generators are really pretty straightforward and pretty simple once you understand the fundamentals of AC generators, which I think we do at this point. At least we're well on the way towards that goal. So once we understand AC generators, there are just a couple of structural differences that we make to AC generators, a couple of changes to turn them into DC generators. So they're really quite similar. Same principles, Faraday's law still applies. We just change a few things about the generator structurally, the design of the generator to produce a DC output instead of our alternating current AC sine wave. So I think that's good news. It's a fairly simple topic today. So since the topic today is pretty simple, I think it's a good opportunity to do some example problems. So that's what I'd like to do in this first video today. So I'd like to start by going over problem set number 14. And then I have a couple of additional problems that I'll go over as well. So I'm going to switch over to the document cam and I'll start by reviewing problem set number 14. All right, here is problem set number 14. The first one says we have an AC generator producing 100 volts AC output. List 3 specific ways that you could double the output voltage. So to answer this, you can look at Faraday's law right here, and you can look at the different terms that we have in Faraday's law. And basically, what could you change over here to double the output voltage, E, or E induced? All right, it only asks for 3, but there are 4 different ways, so I listed all 4 here. So how could you double this? Well, you could double the rotation speed of the rotor on the generator. So imagine this is your armature, and you just need to increase the rotation speed by a factor of 2. So if you double the rotation speed, in that case, you will cut delta T in half. So it will take half as long to rotate from some position on the rotor to some other position of the rotor. So if you cut that in half, then you're dividing by a number that is only half as big, and so your result will be twice as big. So you would double the output voltage. So you can cut delta T in half by doubling the rotation speed, or you can double the number of turns in the coil in. It's pretty clear that if I double in, I would double the output voltage. The other two aren't quite as obvious, but it turns out I could double the strength of the magnetic field, B, or I could double the area of the coil of wire, which is the armature. And both of those would work because the magnetic flux, which is right here, the flux equals the magnetic field strength times the area. And if I double those, it turns out I will also double the change in magnetic flux. So those two aren't quite so obvious, but they're both true. If you double the strength of the magnetic field, B, or if you double the area of the armature, then you will double the change in magnetic flux, delta phi. Okay, so you had to list 3 of these right here for number 1. Number 2 says that we have a coil of wire with 500 turns. It passes through a change of 0.02 Weber. So this is pretty nice because it tells us the change of magnetic flux. We don't have to calculate that. It's already given to us. And that happens in 0.4 seconds. What is the induced voltage as measured at the output leads of the coil? And this tells us what we talked about previously, which is that the magnetic field strength is Tesla, units are Tesla, and the units for flux are Weber. Okay, so here's our equation for Faraday's law, and we are given the number of turns in, and we're actually given the change of magnetic flux this time. Normally we'll have to calculate this, but here it's actually given to us. That's convenient. And we're told delta T is 0.4 seconds. So in this case, all we have to do is plug these in. So don't forget your negative sign. That's an important part of Faraday's law. Negative 500 turns times 0.02 Webers divided by 0.4 seconds. Plug those into your calculator and you get negative 25 volts. So I think I've mentioned this before, but don't be concerned if you get a negative voltage. That's totally fine. Remember that AC sine waves spend half of their time in the positive half cycle and half of their time in the negative half cycle. So if you get a negative voltage, it's no problem whatsoever. You should expect to get negative voltages occasionally. And of course, if you get a negative voltage, you would expect that you'll also get a negative current, which is the subject of the next question. It says the coil of wire in problem number 2 is connected to a load and the total resistance is 5 ohms. So how much current will flow in this coil? Well, this is just a simple Ohm's law equation. We have a relationship V equals IR, and we know the voltage from number 2, and we're told the resistance, so we can find the current. So rearrange this, find that the current is equal to the voltage divided by the resistance, plug in negative 25 volts for the voltage and 5 ohms for the resistance, and you get negative 5 amps for the current. So it's never a problem to have a negative voltage or negative current. Both of those are totally fine. It would be a problem if you got negative resistance. You're never going to have a resistor or anything that has a negative resistance value. So you'll always get a positive resistance, but you can definitely get negative voltage or current. Then we have number 4. We have a coil of wire with 1,000 turns. It's wrapped around in the shape of a 20 centimeter by 20 centimeter rectangle. In this case, actually, it looks like a square. And it's exposed to a magnetic field that changes from 0.0, so that's B1, to 0.6 Tesla, that'd be 0.2, in 0.2 seconds. What is the voltage measured at the output leads of the coil? Okay, that also sounds like a Faraday's law equation because we're given the number of turns and the area. We can get the area from this, and we're given the change in magnetic field and delta T. Sounds like we can plug all of that in and find our induced voltage. So I like to write down what we know first. We know that N equals 1,000 turns. The other thing we know right off the bat is delta T. I actually wrote that down here. Delta T equals 0.2 seconds. And we're given the shape of the armature, so we can find the area with that information. And we're also given B1 and B2, so we can use all that information to find the change in magnetic flux. So that's what we got to do. We know that the change in magnetic flux is equal to B2A2 minus B1A1, but the area of the armature is not changing. So we can factor out the area and just call that the area times B2 minus B1. So now we need to know what is the area. The area, it needs to be in meters squared. So we need to convert 20 centimeters to meters. So we know that 20 centimeters is equal to 0.2 meters. Move the decimal place 2 points to the left, 1, 2, to get it in meters. So we have 0.2 meters times 0.2 meters, which gives us 0.04 meters squared. So plug that in for your area right here. And then we have B2 minus B1. If it goes from this to that, then that's B1 and that's B2. So B2 is 0.6 Tesla and B1 is 0.0 Tesla. That's a T right there. And then we multiply those in our calculator and we get the change in magnetic flux is 0.024 Webers. Now we have everything that we need to plug into Faraday's law. So plug in for number of turns in the coil, change in magnetic flux, delta T, don't forget your negative sign, and you get an induced voltage of negative 120 volts. Number 5 is similar to number 3 a little bit ago, and it says that we have the output of this generator from number 4. It's connected to a load, and the current measured through the load is negative 10 amps, which we should expect because we have a negative voltage, so we get a negative current. What is the resistance of that load? So we can rearrange Ohm's law again to solve for the resistance value. R equals V divided by I. Plug in the voltage, it's negative 120 volts. Plug in the current, it's given as negative 10 amps, and so our resistance is 12 ohms. All right, as I mentioned at the beginning of this video, I think I'll take the opportunity today since the topic of DC generators is pretty straightforward, I think I'll do a couple more review problems because you never really have too many review problems. It's always good to get a little extra practice. So I think I'll go ahead and do a few more review problems in this video. So I've got about 4 more example problems I'd like to show you. So I'm going to flip back over to the document camera, and we'll go over some more example problems. All right, so here are the example problems. So I'm just going to show all 4 problems to you at first, and then I will give you some time to work it out, and then we'll go over them. All right, the first one just says, which direction is this generator rotating? So this is our prototypical simple generator where the armature is on the rotor and the field is on the stator around the outside. And it tells us which way current is going. Current is going into the board or into the page, into the screen as you're looking at it, into the screen on the right side and out of the screen coming out on the left side. All right, so we know which direction our field is going. We know which direction our current is going. So you should be able to tell me which direction the motion is, and thus which direction this armature is rotating. Okay, which direction is the rotor rotating? That's number 1. Then number 2 says which side of the armature is positive and which side is negative at this point in time. We know that if this is an AC generator, then we know that the polarity of the output is going to flip-flop every half rotation. But at this point in time, which side is the positive side? Which output wire right here? This one or this one? Which one is the positive side and which one is the negative side at this point in time? All right, so once again, we know that the direction of the magnetic field is, in this case, actually now from left to right, north to south. And now we know the direction of motion of the rotor. And now you can tell me which way is the current going, and then you can tell me which side is positive and which side is negative at this point in time. That's number 2. Number 3 is material that we talked about last time in the last class. We have, I'm going to hide this. All right, we have this generator right here, and we say that it is spinning the rotor, which has the armature on it. The rotor is rotating at 2,000 RPM. What is the output frequency from this armature? All right, so it doesn't show the slip rings or the connections right here, but just assume that we do have slip rings here. And we know this is rotating at 2,000 RPM. What is the output frequency of the AC voltage? Okay. All right, so that's material from last time. And then the last question that I'll go over in this video is a problem that says we have a generator with a square armature, and it's rotating from a position where the average magnetic field strength is 0.1 Tesla to a position where the average magnetic field strength is 0.7 Tesla in 0.05 seconds. The armature has 400 turns of wire, and the output voltage is negative 300 volts. What is the length of one side of the armature, which remember is square? All right, so what you should do now is pause the video and take a few minutes, or however long it takes you, to work through these problems. These problems, I will tell you, are great examples of what you might find on the next quiz or the next exam. I haven't written either one yet, so I can't tell you exactly what's on either one, but these are definitely the types of problems that I am likely to put on the next quiz and the next exam. All right, so take a few minutes. All right, I will assume that you have taken a couple of minutes and you have solved these problems as best you can. So let's go through them. Number 1 says, which direction is this rotating? And we've got a generator here that has 2 poles, and it's got an armature on the rotor. And so if this is a question that is relating the polarity of the magnetic field to the direction that current is flowing to the direction of motion, well, that sounds like a right-hand rule problem. So we have to break out our right hand and put it into the shape that we need, where your thumb, first finger, and second through fourth fingers are all perpendicular to each other. And then we just got to figure out how to orient our hand such that it matches up with the situation. All right, so we know that our field is going from right to left, north to south, from right to left. So we know our first finger is going to have to be pointing to the left. And then we know that our current, I'm going to do this wire first. Our current in this wire is going into the board, into the screen. So my second through fourth fingers are going to be pointing into the screen. They're pointing down into the screen or into the table as I'm looking at it. And so you can see my thumb is pointing down towards the bottom of the page. All right, so my thumb represents the motion, and it is pointing down towards the bottom of the page. So I'm going to go ahead and draw that in here in a different color. So at this point in time, the right side of the armature is headed down towards the bottom of the page. Now I would anticipate that the other side of the armature is going to be doing the exact opposite, and let's go ahead and try that and see if that's true. All right, so once again, the field is going from right to left, so my first finger goes to the left, and now the current is coming out of the page towards you. So my second through fourth fingers need to be going up towards you, towards the camera. And now if I orient my right hand, it looks like my thumb, representing motion, is pointed up towards the top of the page. All right, towards the top of the page. All right, so if this side of the armature is headed up and this side of the armature is headed down, then this armature must be rotating like this, around in a circle like this. All right, and if we think about this direction of rotation, this is clockwise. So this first generator is rotating in the clockwise direction. Okay, that's number one. Number two says which side of the armature is positive and which is negative at this point in time. All right, so once again, we're given two things and we're asked to find the third. We're given the motion and we're given the direction of the magnetic field. And now we're going to try to find the current, because once we find the current, then we can figure out which is the positive side and which is the negative side. All right, because we know current goes from positive to negative. All right, so first thing I'm going to do is say, all right, if this thing is rotating counterclockwise, then at this point in time, this side of the armature is headed down and this side of the armature is headed up. All right, so now I know the direction of motion of these wires in the armature, and now I can go ahead and apply my right-hand rule. All right, so I'm going to go ahead and apply the right-hand rule to this side first, and then I'll do it to the left side. So on the right side, the field is going from left to right, so my first finger is going to point from left to right, and then the motion of this wire is up toward the top of the page, so my thumb needs to point up toward the top of the page. So that leaves my second through fourth fingers pointing down into the page or into the table, away from you. All right. So the current here is going like this. That represents into the page. And now I apply the right-hand rule to the left side of the armature. My thumb is going to point down. Oh, I'm going to have to contort my hand here. My thumb has to point down. My first finger needs to point from left to right. So that means my second through fourth fingers are pointing up towards you or out of the page. All right, so we draw that like this. All right, so good. When you do this, your direction of current flow on either side of the armature should be opposite, because we've got current flowing continuously in a loop from this side of the armature around and then out of this side of the armature. All right, so if I connected this armature like it would be in the real world, I would have slip rings, which I think I'm not going to try to draw. They're kind of tough to draw, but I would have slip rings. I'm just going to draw them as little dots for connections for right now. So I would have a slip ring connected to this side of the armature and a brush riding on that slip ring. And I'd have a wire from that brush. And then on the other side of the armature as well, I would have a slip ring connected to this side of the armature. And then I'd have a brush riding on that slip ring. And then I would have a wire connection from that brush. All right, so these are my connections. And then I would have some load, which would be like the grid, the electric grid, which I'm just representing by a resistor right here. So if current is flowing out of the page on the left side of the armature, it's going to continue going in this full loop right here. This is a circuit. So it's flowing in this circuit right here, round and round this circuit. So current is flowing out of the left side of the armature. It's flowing this direction. It's flowing from left to right, the way I've drawn it, through this resistor. And then it's flowing this way back into the armature. All right, and we know that current, by definition, flows from positive to negative. And current is flowing from this side of the generator through the load and back into this side of the generator. So if it's flowing from this side to this side, and we know that the current flows from the positive to the negative, that must mean that this side is the positive side and this side is the negative side of the armature at this point in time. We know that since it's an AC generator, it's going to flip-flop. The polarity is going to flip-flop, and it's going to go into a negative half cycle after half of a rotation. But at this point in time, the way that I've drawn it, this is the positive side, and this is the negative side of the armature at this point in time. All right, so that was number 2. And then number 3. Okay, here's number 3. It says this generator is rotating at 2,000 RPM. So this is the rotor. The armature is on the rotor, and it's rotating around at 2,000 RPM. What is the output frequency? All right, so remember from our last class, we have a relationship between the rotation speed of the rotor and the number of poles on the magnetic field and the output frequency. And that relationship looks like this, where N is the rotation speed of the rotor, and 120 is just a conversion factor, F is the output frequency, and P is the number of poles on the magnetic field. So look at this and the question, and what do we know? We know that N is 2,000 RPM, that's how fast the rotor is spinning. And we know P, the number of magnetic poles on the magnetic field. All you gotta do is count them. 1, 2, 3, 4. Also, one more thing I'll point out here. Notice that the magnetic poles have to alternate. They have to go north, south, and back to north again. All right, so if you had clearly this is a 4-pole magnetic field, 1, 2, 3, 4, but if you had a 6-pole magnetic field, they would still have to alternate. They'd still have to go north, south, north, south, north, south. If you had an 8-pole magnetic field, they'd still have to alternate. It has to go north, south, north, south, north, south, north, south. It has to alternate. All right. Otherwise, if you have 2, say, north poles right next to each other, they just function as one combined larger north pole. So in order to get that alternating current, you have to have alternating magnetic poles. Okay. All right, enough of that. Let's go ahead and fill in our numbers here. So N is 2,000, P is 4, and we want to solve for F. So we know what N is, we know what P is. Now I'm going to rearrange this equation and solve for F. So to get that, I'm going to multiply both sides times P and divide both sides by 120. So I get F equals N times P divided by 120. And now I can plug in numbers. F equals 2000 RPN times 4 divided by 120. Plug that into your calculator and you get the frequency is 66.67 hertz, which is not a very common output frequency at all. That's not a standard frequency that I've ever seen used on any type of system, but that's not really the point. The point is that if you had this generator right here and if you had 4 poles and it was spinning at 2000 RPM, then this is what you'd get. Your output frequency would be 66.67 hertz. All right, and the last one is this. We have a generator, we have a square armature, that's going to be important, and it's rotating from a position where this is the initial magnetic field strength, so that's B1, to this point where we have this average magnetic field strength, so that's B2, in this amount of time, so that's delta T, and it says we have 400 turns of wire, so that's going to be N, and it gives us the output voltage, so that's going to be E induced. All right, so we have all these variables, and we're trying to get a relationship between the magnetic field and the amount of time it takes for it to rotate, for the armature to rotate, or for the rotor to rotate. And we're given the number of turns of wire and E induced, so this clearly looks like a Faraday's law problem. All right, so we have all these relationships, so let's go ahead and write out Faraday's law, and then think about what we know and what we don't know. So here is Faraday's law. And what do we know? Let's go ahead and write down everything we know. We know E induced, it's negative 300 volts. We know N, it's 400 turns. We know delta T, it's given to be 0.05 seconds. What is the change in magnetic flux? Well, we don't quite know that yet, but we know some things about the change in magnetic flux. We know that the change in magnetic flux is equal to the area of the armature times B2 minus B1, and this is what was given for B2, and that's what was given for B1. So we know something, and we can simplify that. 0.7 Tesla minus 0.1 Tesla is 0.6 Tesla. So this is our change in magnetic flux. It still has a variable in it, that's A, but if we can solve for A, then maybe we can solve for the side length of the armature. All right, so we know everything in Faraday's law except A. So let's go ahead and plug that in. Plug in for E induced, plug in for 400 turns for N. Don't forget your negative sign there. That's from the basic equation. We plug in for the change in magnetic flux, and we plug in for delta T. And now you see that the only unknown here, the only variable is A, the area of the armature. So we can solve for that. Solve for A. Remember that when you solve for A in Faraday's law, the units for A are going to be meters squared. All right, so we can solve for that. The way we would do that is we would divide both sides by negative 400 turns. We multiply both sides times 0.05 seconds, and we divide both sides by 0.6 Tesla. And if you plug all that into your calculator, you'd get the area equals 0.0625, and the units are meters squared. That's what the units always are for area in Faraday's law. Okay, so we know what the area of the armature is, and it tells us in the problem that it is a square armature. A square has 4 equal side lengths, right? So we know the area, and we know it's a square, so with that, we can solve for one side length of the armature. So here's what we got. We've got a square armature that looks like this. Here's our armature. And we know that it has an area of 0.0625 meters squared. And we know that it has equal side lengths. And I just called them lowercase l. You can call them whatever you want. So I know that the area of a square equals the side length squared. And in this case, I know the area of this square is 0.0625 meters squared, and I set that equal to the side length squared. Now, if I want to solve for L, it asks for what is one side length. So I want to solve for L, not L squared, but L. So I can do that by taking the square root of both sides. L is going to equal the square root of this, square root of 0.0625 meters squared. And you plug that into your calculator and take square root, and you get the side length is 0.25 meters. Remember, if you take the square root of meters squared, you're going to get meters. All right, so the side length is 0.25 meters, which is the same thing as 25 centimeters, so either one of these is correct. So that's what we've got. That's the side length for one side of the square armature. All right, so I hope these example problems were helpful. These are very characteristic of what you might find on the next quiz or the exam, like I mentioned. Hopefully those all kind of made sense. I think at this point you should be able to do those, especially after I went through them. I think that you should be able to do all of those by yourself fairly quickly, you know, in a matter of a couple of minutes each. All right, so I think I'm going to go ahead and stop this video, and I will start a new video to talk about DC generators. So I'll see you in the next video.